Okay, so in this video I'm going to have a look at hyperbolic functions, and in particular I'm going to have a look at Cosh of t and Sinh of t, or Sinh of t. So I have the two formulae here. Cosh of t is e to the power of t plus e to the power of minus t over 2. Sinh of t is e to the power of t minus e to the power of minus t over 2. So what I'm going to do in this video is look at the derivation of these two formulae. So where I'm going to start here is with the unit circle. So the first thing I'm going to do is just draw a radius. So we're going from here to here, and this point here then is going to be x, y. And polar form, it's going to be cos theta, sine theta, given that this is theta here. So when we look at xy here, we know that this distance here is going to be y, and this distance out here is going to be x, where x is going to be cos theta, y is going to be sine theta. I did that in a previous video. The sine of theta is y over 1 in this case because the radius is 1. So if sine theta is y over 1, sine theta is y. That's why we have sine theta here. Cos theta is x over 1, or cos theta is just x. Now if just to go off on a bit of a tangent here, if the radius wasn't 1, if the radius was 5 for example, then we would have polar coordinates 5 cos theta, 5 sine theta. But anyway, let's continue on. We have x and y here. Now what I want to do first of all is just talk about this area here, the area of this sector here. Now the area of that sector is going to be the proportion of the sector multiplied by the area of the circle. So the proportion of the circle, it's going to be theta over 2 pi. 2 pi is the area of the entire circle. It's not the area of the entire circle, it's 360 degrees. Theta is the angle we're talking about. So theta over 2 pi is the proportion of the circle that we're talking about. Now the area of the entire circle in this particular case is, the area is just going to be pi or squared. In our case, or is 1, so it's going to be 1 squared. So the area of our circle here is just pi. So we've got to multiply this by pi. The 2 pi's will cancel and you just end up with theta over 2. So what does this tell us? This tells us that our input here and here, these inputs here, are twice the area here, twice the area of this sector. I'm going to use that when we come over here to our hyperbolic function. So, by the way, I should mention here as well that this is a circle, so the equation of a circle is, of course, x squared plus y squared is equal to 1 when the center is 0, 0. Okay, so that's our trig, or circular trig function, if you like. Let's have a look at our hyperbolic function over here. Now, this particular function here is x squared minus y squared is equal to 1. So what you can do, in fact, is put this in as x, this in as y, and you will find you'll get 1. I might actually do that in another video. But this is our hyperbolic function. There is another section to this, by the way, out here. I haven't drawn it in. It would look something like that. It's just really a mirror image in the y-axis here of the right-hand side. So this is the unit hyperbolic function, so we have 1 unit out as far as here. Let's take a point up here and let's call that xy. So we have the distance out as far as here is going to be x, and the distance up along here is going to be y. And in fact, the distance out along here, x, is also Cosh of t, and out along here we've got the Sinh, or the Sinh, I should say, whichever version you like, the Sinh of t. Now what I'm going to do is draw a line down along here to the origin, and what we're going to do in this case is have a look at this particular area here, this green area here. I'm just going to call that, maybe, let's call it area 1, and this is area 2 in here. So what you'll actually find again here is that this area here, let's call our area t over 2. So this area here, the green area here, is t over 2. Now there is a proof to show that t over 2 is the area, but I'm not going to get into that in this video. I might do it in a separate video. So that would mean that the t is just going to be equal to twice the area. So what does that mean? That just means that our input into here and here, our input into Cosh and Sinh or Shine, is twice the area. It's not an angle anymore as such. So we're going to get Cosh of twice the area, Shine of twice the area here to work out these values here. So what we want to do is prove these two formula up here, or derive these two formula up here. So what we want to do is get x and y in terms of t. So x is Cosh of t, y is Shine of t, so all we've got to do is get x in terms of t and y in terms of t. So that's what I'm going to do in this particular video here. Okay, so let's start into the procedure for the derivation of these two formula here. Okay, so what do we have so far? We have A1, which is this area here, this area in green, and we have A2, which is this area here. Both of those together are going to add up to make this right-angled triangle here. Now, a right-angled triangle consists of a distance from here to here, from the origin out to here of 1, and then a distance from the origin out to here of x, a distance from here up to here of y, and y is just going to be the square root of x squared minus 1. So I'll just show you that down here. The equation of our curve is x squared minus y squared is equal to 1. That'll give us minus y squared is equal to minus x squared plus 1. Change the signs, y squared is equal to x squared minus 1, and then finally y is equal to the square root of x squared minus 1. We're going to just take the positive version here because we're dealing in the first quadrant. Okay, so that's where this square root of x squared minus 1 comes from. Now, first thing we're going to do is just have a look at A1 and A2 here. If we add those together, that gives us the area of our triangle, which is half the base times the height. So the area of, let's say, A1 plus A2 is going to be half of x times the square root of x squared minus 1. So what we want is the area underneath the curve here, underneath the red curve, and that is A2. So we're going to have a look at that. That's just going to be this last expression minus t over 2, which is area 1. So A2 is going to be equal to half of x times the square root of x squared minus 1, all that minus t over 2, which is area 1. So let's just write that out. So area 2 is going to be equal to half x times the square root of x squared minus 1 minus t over 2. And this is just a total, if you like, minus area 1. Okay, so we have area 2 here, an expression for it. What we're going to do now is look at finding another expression for area 2, equating these two expressions, and that should hopefully bring us where we want to go. Okay, so let's have a look at working out area 2 a second way. So the way we're going to do that is just go back up here and look at our function in the first quadrant here. Our function in the first quadrant here is y is equal to the square root of x squared minus 1. What we're going to do is integrate that function between 1 and x. That should give us area 2 here. So let's do that. Okay, so we have area 2, which is going to be the integral from 1 to x, square root of x squared minus 1 dx. Now we're going to do this by substitution, so what we're going to do is let x equal to sec theta. Now if we do that, we get the square root of x squared minus 1 equal to the square root of sec squared theta minus 1. Sec squared theta minus 1 is just equal to tan squared theta. That just gives us the square root of tan squared, which is just tan theta. Now, just looking at our limits, we've got sec theta is equal to 1, and we have sec theta equal to x. If sec theta is equal to 1, we've got 1 over cos theta is equal to 1. That just gives us cos theta is equal to 1, or theta is equal to 0. if we have sec theta equal to x, the upper limit, that just, there isn't a whole lot we can do with that. Really, we've just got sec inverse x equal to theta. So let's just look at the dx then. So we know that again x is equal to sec theta. If we differentiate, dx d theta is equal to sec theta tan theta. And then if we multiply across by d theta, we get dx is equal to sec theta tan theta d theta. This differential here is just a standard differential. And we will actually use this later on in this integral as well. That's it. We've got, let's just substitute in our bits and pieces here. This was our integral up here. We did some substitution. So we now know that area 2 is equal to the integral. Our limits are 0 to sec inverse x, that's here, and we've got our square root of x squared minus 1, which is tan theta, and then we have our dx, which is sec theta tan theta d theta. Now we can just tidy that up a little bit. We've got 0 to sec inverse x. We've got tan squared theta sec theta d theta. Okay, so what we've got to do next really is just integrate by parts. So let's start that process. Now our integral by parts then is going to be the integral of u dv is equal to uv minus the integral of v du. The way we're going to do this is we're going to let u equal to tan theta. I'm going to let dv equal to tan theta sec theta. So we have our tan here and our tan here. That'll give us our tan squared here. And then we have our sec theta here, which is this bit here. So let's just differentiate down the left here and then integrate on the right. So let's do that. So we have du d theta. If you differentiate tan, you get sec squared theta. Multiply across again, you've got du is equal to sec squared theta d theta. Now on the right here we're going to integrate. So if you integrate dv, you'll get v. If you integrate tan theta sec theta, remember we had that a few minutes ago. If you differentiate sec theta, you get tan theta sec theta. So if you integrate tan theta sec theta, you'll get sec theta. So that's kind of handy. Now let's just substitute all of that back into our integral here. So let's do that. Okay, so we have u times v. So let's do u times v. Well, u is tan theta. V is sec theta. Our limits are 0 to sec inverse x. And then we've got to subtract the integral, again from 0 to sec inverse x of v du. Well, we've got sec theta is the v, and then the du is sec squared theta d theta. Okay, so this is our substituted integration by parts. Let's substitute in our limits now. So we've got, let's see, we have tan of sec inverse x, and then we've got sec of sec inverse x minus, we've got to put in the 0 now, so it's going to be tan of 0 sec of 0. Now we've got to subtract this integral here. What I'm going to do here, I'll just put in the limits first, sec inverse x. What I'm going to do here is swap out that sec squared theta, and I'm going to put in 1 plus tan squared theta just to make it easier. And I have another sec theta here, d theta. Okay, so let's see what we can do with all of this. We have tan of sec inverse x. We know that sec inverse x is just theta. So this here really is just theta. This here is just theta as well. So if we look at, we need the tan of theta, So let's have a look, just to go off on a little bit of a tangent here. We know that sec inverse theta, sec inverse x I should say, is theta. That's the substitution we made at the beginning of this integral. So sec inverse x is equal to theta. So in other words, sec of theta is equal to x. That was the original substitution we made actually. Sec theta is equal to x. Now sec is just 1 over cos theta is equal to x. That just means if we flip these two upside down, you're going to get cos theta is equal to 1 over x. If you were to draw a right angled triangle, put our theta here, this is right angle here, we have cos theta is equal to 1 over x. That means 1 would go here, x is there, and our opposite then would just be, using Pythagoras' theorem, you would get the square root of x squared minus 1. So our tan of theta is going to be the square root of x squared minus 1 over 1. So that's going to be what we're going to put in here. Okay, so let's do all of that. We have, let's see, we have tan of sec inverse x. So that's tan of theta. That's just all going to become the square root of x squared minus 1 over 1. And then we have the sec of the sec inverse of x. Now, if you think about that, for example, if you think about, let's say, the sine, for example, of 30 degrees. Again, maybe I'll do this in a different color again. Let's say you have the sine of 30 degrees. We know the sine of 30 degrees is just a half. That means the sine inverse of a half is equal to 30 degrees. Now, if you get the sine of the sine inverse a half, so that there is just 30 degrees. Really, you're just getting the sine of 30 degrees, which again is a half. So the sine of the sine inverse of a half is just a half. Similarly here, we have the sec of sec inverse x, so that's just going to be equal to x. So we also have, let's see, the tan of 0. The tan of 0 is just 0. So all of this is just going to become 0. And then we have minus this integral here. This integral is just going to be, if we multiply out the sec theta by 1 and the sec theta by tan squared theta, we'll get the integral from 0 to sec inverse x of sec theta, d theta, I'll just split it up, minus the integral from 0 to sec inverse x of tan squared theta, sec theta, d theta. Okay, so let's just move that on down a bit. Now, if you look at this here, this is just what we started with. This is just A2. This is just area 2. This is the integral that we started with at the beginning when we started doing integration by parts. So really what we've got here is we've got the square root of x squared minus 1 times x. So I'll write that down anyway. Square root of x squared minus 1 times x minus the integral of sec theta. If you integrate sec theta, you'll get log of the absolute value of sec theta plus tan theta. Again, that goes from 0 to sec inverse x, and then we are subtracting area 2 here. Remember, this is area 2. Okay, so let's just put in our limits here again. So we have area 2 is equal to the square root of x squared minus 1 times x minus, if we put in sec inverse x here, we've got the log of, we've got the sec of theta, so it's the sec of the sec inverse x, which is just x, and then we have the tan of sec inverse x, and we had that a few minutes ago as well. We know that that's just the square root of x squared minus 1. And then we've got to subtract, well, we've actually got to subtract 0 because, let's see, we have the sec of 0, which is 1 over the cos of 0. The cos of 0 is 1, and the tan of 0 is 0. So really it's just a log of 1, so that's just going to be 0. Now out here then we have a 2 again. Okay, so let's keep going. We have a 2 is equal to the square root of x squared minus 1 times x minus this log here. This log is just going to be positive, so I'm just going to leave it as it is. Log of x plus the square root of x squared minus 1 minus a2. What you can do here, you can see you've got an a2 on the right hand side and a2 on the left hand side. So what I'm going to do is, if you bring this over to the other side, you get two a2's, and then divide across by that 2, you'll get area 2 is equal to a half of all of this here. Square root of x squared minus 1 times x minus log x plus the square root of x squared minus 1. And that's the end of our integration, if you like. So this is our second equation for area 2. Okay, so I have the two expressions here equated, so let's just solve for x. Let's multiply this out first. We've got a half square root x squared minus 1 times x minus a half log x plus the square root of x squared minus 1 is equal to a half x times the square root of x squared minus 1 minus t over 2. So you can see here that we've got a lot of halves that we can divide across by, so that half will disappear, that half will disappear, that half will disappear, and this half here will disappear as well. Also on the left hand side we have the square root of x squared minus 1 times x, and we have square root of x squared minus 1 times x on the right hand side as well. So if we bring one over to the other side, or subtract from both sides, this will disappear as well. So what we'll be finally left with here is minus the log of x plus the square root of x squared minus 1 is equal to minus t, or just t is equal to the log of x plus the square root of x squared minus 1. Okay, so let's try get x on its own here. So what we've got to do first is change from log form to index form. So I'm going to write e to the power of t is equal to x plus the square root of x squared minus 1. Next thing I'm going to do is just subtract the x. And the next thing I'm going to do then is just get rid of that square root. We're going to square both sides. So if we square the left hand side, we get the square of e to the power of t, which is e to the power of 2t. If we square the x, we'll get x squared. But we multiply these two together and multiply by 2. So it's going to be minus 2e to the power of t x plus x squared is equal to x squared minus 1. Next thing I'm going to do is just get rid of these x squared, subtract x squared from both sides. I'll be left with e to the power of 2t minus 2x e to the power of t is equal to minus 1. Okay, next thing I'm going to do is bring over the e to the power of 2t, so I've got minus 2x e to the power of t is equal to minus 1 minus e to the power of 2t. Let's just get rid of all those minuses. 2x e to the power of t is equal to 1 plus e to the power of 2t. Next thing I'm going to do is just divide by e to the power of t. Got 2 to the power of x here is 1 plus e to the power of 2t divided by e to the power of t. Now let's just do that. If we divide in the e to the power of t, we'll get 1 divided by e to the power of t, which is just e to the power of minus t. If we divide here, e to the power of 2t divided by e to the power of t, subtract the powers, and you're just left with e to the power of t. And then finally we have our x. We have e to the power of t, which I'll put first, e to the power minus t over 2. So this is our formula that we wanted to derive, and this is Cosh of t. Okay, so we have our first formula derived. Let's have a look at the second one then. Second one is going to be sine of t. So let's start with, we know that y is equal to the square root of x squared minus 1. Okay, so let's substitute in our x here. So this will give us y is equal to the square root of e to the power of t plus e to the power minus t over 2. All of that we need to square and then subtract 1. So let's just square that out. So we get e to the power of 2t plus 2 e to the power of t e to the power minus t plus e to the power minus 2t. That's going to be all over 4. And then we've got to subtract 1. Next thing we're going to do is just add those two fractions. Just turn all that into one fraction. So it's going to be all over 4. So we got e to the power of 2t. So this here will just give us 2, because e to the power of t times e to the power of minus t will give us e to the power of 0, which is 1. 1 times 2, 2. Then we've got plus e to the power of minus 2t, and then we have, this is over 1 here, so this is just going to become minus 4. Okay, so we have y is equal to the square root of e to the power of 2t minus 2 plus e to the power minus 2t over 4. Let's just get rid of that square root from the bottom part of this fraction. We can square root the top anyway, and we can square root the bottom. The square root of the bottom is 2, so we just end up with a half. And then we have the square root of e to the power of 2t minus 2. Actually, I'm going to change this. You'll see why in a minute. I'm just going to change that back to e to the power of t, e to the power minus t. Remember, this is just 1 here, so it's not going to change the minus 2. And then we've got plus e to the power minus 2t. So let's just finish this off. Now we have half the square root of, you can see that this factorizes to e to the power of t minus e to the power of minus t squared. Because e to the power of t will give us e to the power of 2t, minus e to the power of minus t squared will give us e to the power of minus 2t squared, and then if we multiply these two together and double it, we'll get this one here. So we have the square here of a square root. So finally we end up with y is equal to e to the power of t minus e to the power minus t, half of that, which is over 2. This is our final answer here for y, and this is sine of t. The final part of this video I want to have a look at is tan of t. So tan of t is just going to be sine over cosh. So it's really e to the power of t minus e to the power minus t over 2 all over e to the power of t plus e to the power minus t over 2. So if we just flip the denominator and multiply, the 2's will cancel, and we'll get e to the power of t minus e to the power minus t over e to the power of t plus e to the power minus t. Now dividing above and below the fraction by e to the power of minus t, we'll get e to the power of t over e to the power minus t minus 1 over e to the power of t over e to the power minus t plus 1. So if we just simplify this, then we get e to the power of t divided by e to the power minus t. Subtract the powers, that's e to the power of t minus minus t, e to the power of t plus t, or e to the power of 2t minus 1. Same on the bottom, e to the power of 2t plus 1. And this is our formula for tan of t.